Okay, I guess it is doing, yeah. All right, today's topic is network simplex, as I just mentioned, right? Now, it is, again, a simplex algorithm, but it's specified so that it works only on networks where we have, remember this special structure, special A matrix, this null dark incidence matrix, and we're just sending flows from supplies to destinations with minimum total cost. That was the structure of the minimum network call problem. And network simplex algorithm is actually specially designed to solve that problem. That's why we were actually last week learned how to convert another problem to the format of MCNFP so that we can utilize the methodology developed for MCNFP. And the methodology is what we will be seeing today, which is network simplex algorithm. It is, as I said, again, a simplex algorithm. We will have an improving direction. So we enter a non-basic variable and we will have a ratio test and we will kick one of the basic variables out from the basis, whoever reaches the bounds first. But the structure, as you're going to see, is a lot easy to construct and follow. All right. So again, we're going to look for basis, right? So the most important, the very first property of a basis as being linearly independent, so that we take the inverse and X becomes B inverse B, right? So we're going to look for linearly independent columns in our dark incidence matrix, or which represents our graph actually. So it's easier to see over the graph. So that's what we're going to do. Now, our A matrix, we're again trying to solve, remember, we're trying to solve what sensitivity analysis? Sorry. We're trying to solve minimizing CX subject to hold on. It's early and I didn't get my coffee yet, but I'll be here. Okay. Minimizing CX subject to X equals B, X between bounds, right? This is the problem that we're trying to solve. And again, we're going to look for, and this A matrix is our node arc incidence matrix. It's a special matrix because it represents this graph here, right? This graph here. And we have BIs, positives and negatives. That's the special structure. So, okay, then we first have to come up with the structure which will represent my linearly independent columns. Yeah. In the standard simplex, we were setting M of those, right? So how about it's going to be in here? How is it going to be in here? We will first have a couple of observations regarding the graphs, and then we will see what it is. So let's look at a cycle in a graph. So these red arcs in this graph represents a cycle. Careful, they're not directed. But when I mean, like for example, 1, 3, 3, 2, 2, 4, 4, 1, right? This is my cycle. They're not in the same direction. I don't care. But those red arcs do form a cycle in this graph, right? Now, let's look at the columns of that cycle. Remember the structure we were having in the node arc incidence matrix? We were putting a plus in the tail and minus in the head, because plus was representing the supply and minus was representing the demand. And this arc was sending something from his tail to the head, right? This was the structure. So the columns representing those arcs those red arcs, the ones that I designed as my cycle, are arc 1, 3, arc 1, 4, arc 2, 3, and arc 2, 4. Okay? Now, and these are the columns in the node arc incidence matrix. Arc 1, 3 has a 1 in 1 and a minus 1 in 3 and zeros elsewhere. Arc 1, 2 has a 1 in 1, 1, 4, and a minus 1 in 4 and zeros elsewhere. That is how we actually constructed the node arc incidence matrix. And these are the columns representing those arcs then, right? Each column has only 1 plus 1 and a 1 minus 1. Everybody else was 0. That's the special structure of this network's actual MCNFP problem, right? Now, when I take those 4 columns Okay, are they linearly independent? This is the question. Now look at what I find out in here. Just put a +1 in the ones in the same direction and a -1 in the reverse direction. So I consider, let me clean this mass, and I consider the direction of the first arc, which is 1, 3, as the direction of the cycle. So I put a +1 in here. Then this one is a -1. This one is another +1, and this one is another -1. Now, if you multiply each arc, each column of the arc with that plus or -1, you're going to get a vector of zeros. So apparently, they're not linearly independent. Those 4 columns, which forms a cycle, are linearly dependent of each other. This is very important, okay? This means my bases cannot be a cycle, cannot contain a cycle, because the arcs of a cycle will always be linearly dependent of each other. All right? This is really crucial. That means in the MCNFP problem, when I'm trying to solve the MCNFP problem, my bases cannot be cycles and cannot contain cycles. All right? That means this is our first observation. Okay. I cannot even have a cycle in my basis. Now, the other, sorry. Then let me define something for you. Over a graph, any subgraph, some set of arcs in the graph, which are connected to each other, and no cycles, then it's called a tree. All right. So we have a graph, and over the graph, now we're going to select some arcs. And remember, I'm trying to find the basis, right? And we have just seen that cycles are dependent, linearly dependent. So I cannot have a cycle. That brings us to this definition: anything in a tree anything in a graph which does not contain any cycle and connected, so the arcs cannot be one there, then it's called a tree. All right. And we actually look for a spanning tree, because spanning tree is the tree which touches all the nodes of my graph. All right. It doesn't have any cycle because it's a tree, and it's touching all the nodes of the graph. This is important. That thingy is called the spanning tree of the graph. All right. Now be careful. If my graph has n nodes, let's just draw something in here. Suppose this was my graph on 4 nodes. All right. Let me also put the directions. It doesn't matter, but our arcs do have directions. So if this is my graph, now, for example, the arc's direction is different. So this is a tree. The thing in here is a tree. It's not a spanning tree. In order to be, for example, by the way, these 2 arcs do not form a tree because they're not connected. All right. But if I add this one too, now I have a tree and I have a spanning tree, because this tree touches all the nodes of my graph. Now observe, my graph has 4 nodes, my made up graph, and my spanning tree has 3 arcs. That's what's supposed to be. I have to touch all the nodes, and I shouldn't have a cycle. All right. The 4th arc in here will create a cycle. Any 4th arc, try adding one thing here. Let's add this arc. Oops, cycle. This one, cycle. This one, boop, 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 the cycle with everything. All right. So graph, that brings us here to this observation. Any graph on n nodes will have n-1 arcs in the spanning tree. Okay? So we have learned a couple of things up until now. First of all, we have learned that the cycles in the no-dark incidence matrix of matrix A are linearly dependent of each other. They're not linearly independent. So my basis in the algorithm cannot contain a cycle. So anything which is connected but not having a cycle is called a tree. And if this tree is touching all the nodes of my graph, that is called a spanning tree. And a spanning tree of a graph will have number of nodes minus 1 edges. All right? These are the things that we have accumulated for this algorithm. Oh, here we have some nice drawn examples. Suppose this is the graph, the one on top. Yeah, I have 5 nodes. That means my spanning tree will have 4 arcs, right? So let's look at the first one. It is a 1, 2, 2, 4, 5, 4. This thingy is a tree, yes. It is connected, and it does not contain any cycles. But it is not a spanning tree because it's not touching node 3. Node 3 is left out. My spanning tree should be touching all my nodes, okay? So this is a tree, but not a spanning tree. The one underneath, on the other hand, is again a tree, 1, 2, 2, 4, 5, 4, and 3, 4, but it does not contain any cycle. It thus touches all my nodes. So yes, this one is a spanning tree. Any questions? Because these are new definitions. I don't think you have seen these in your previous math classes. If you have any questions, you can write it in the chat board, or you can raise your hand, or you can immediately talk. All right. I'm assuming it's going on well then. Now, a couple of more definitions. The slides start with from the 0th line out there. How do we form a spanning tree then? Given a graph, apparently these spanning trees will be important, right? Now, that's why I'm teaching you those. So, given a graph, how would you form a spanning tree? The idea is, all right, you just start adding arcs, one at a time, as long as they don't create cycles. Let's do that in my fictitious graph here. Let me delete the thingy here. So this is this ugly thing on 4 nodes is my graph. I'm trying to create a spanning tree of this graph. All right. First of all, I'll put my nodes, oopsie, not arcs, but nodes, hanging out there, because at the end, I need a spanning tree. That means I have to touch all my nodes, right? So just to remember not leaving one aside, I'm just drawing them first of all. The algorithm says start adding arcs arbitrarily. Doesn't matter, right? All right, let me start adding this guy. Okay. Do I have a cycle? No, it's just 1 arc. Then, okay, I can add one more. It says start adding arcs arbitrarily. Until when? Until I have 3 arcs. Because this is a graph on 4 nodes, I know my spanning tree will have 3 arcs. I'm supposed to add 3. So this is 1. Which one should be the second one? Let's add, I don't know, let's add this one. Okay, I have 2 arcs. It doesn't create a cycle, so I can add that. I need one more. I need 3 arcs. Now, can I add this arc? No. If I add this, I got a cycle, so no. How about this arc? Anything else doesn't create a cycle, and I'm supposed to touch this one, which is left alone anyway. So if I add, for example, this arc, good. This is no cycle, no cycle. Each node has been touched, and I have 3 arcs. So this is a spanning tree, all right? So finding a spanning tree, you just add 1 arc at a time until you have n minus 1. Be careful not to create any cycles. All right, next. Oh, here is, so for example, for this graph on the right, all right, a spanning tree is on the left. Be careful, the graph has 5 nodes, so the spanning tree should have 4 arcs, and the one on the left does have 4 arcs. A very important observation, and all these observations are actually built up our algorithm. if you have a tree, pick up 2 nodes on the tree. All right, there is a unique path, only one way to reach from one to the other. The direction is not important. All right, so let's look at the one on the top. So let's say from 1 to 4. How do you reach 1 to 4? It's 1, 2, 2, 3, 3, 4. How about from 4 to, I don't know, 5? 4, 3. Well, it's a 3, 4, 2, 4, 2, 5. That's why I said the direction is not important. But there is only one way. All right. Otherwise, we will have cycles. That's the reason. Since the tree does not have any cycles, given 2 nodes of the tree, there is a unique way. All right. And one more important observation on the tree or spanning tree, if you add one more arc, one more, and you will definitely have a cycle. Definitely. And a unique cycle, by the way. Each arc will create a unique cycle. Let's look at this one. That's drawn. So for the tree that's on top, we just added arc 2, 4. And what is the cycle? 2, 3, 3, 4, 2, 4. This thingy here now become a cycle. Let's add another arc. Let's say we're adding, I don't know, do we have this? Yeah, let's add this arc. Okay. If you add this arc, look at the cycle. 2, 3, 3, 4, 5, 4, 2, 5. It's a cycle, unique cycle. All right. Change the color, add one more arc. Let's say we're adding this 1, 3. Yeah. Then I have this cycle here. Unique cycle. Each arc creates exactly one cycle over a spanning tree. This is, again, very important. So for 2 distinct nodes, there is a unique path in the spanning tree. And if you add one arc to your spanning tree, you will create a unique cycle. All right? Any questions? Am I going too fast? Because these are new for you. No question. All right. We have already seen this. Now that brings us to our theorem. This is all the things we've done in the last 15 minutes was actually to come to this point. All right. We need to. You guys are following me, right? Because somebody else is trying to enter the room as the teacher. That's what Zoom says. Okay. Is there any problem in your screens, guys? Somebody write to the chat board, please. No, thank you. Thank you. Okay. Then we're going on. Someone else is trying to barge into our class, but he or she won't be managing this because I'm not clicking. Okay. Anyway, sorry for the thingy. All the observations, definitions was for us to come to this theorem. Remember, I'm trying to solve the minimum cost network flow problem. Minimize Cx subject to Ax equals to B and expect between the upper bounds and lower bounds, all right? But this A is my node arc incidence matrix. It's a very special matrix. For this problem, let me write it. Minimize Cx subject to X equals to B and X is between the bounds. But this A is my node arc incidence matrix. All right. Now, in order to solve this, I'm trying to solve this with network simplex algorithm. Here is the theorem. A collection. Now, remember my basis. I'm trying to find a basis, yeah? And the basis is actually my collection of columns. Which variables represent my basic variables? All right? Now, the theorem says if your matrix is a node arc incidence matrix, okay, your basis is a spanning tree of your graph. All right? Okay, spanning tree. So no cycles, touch every node, n-1 arcs. This is crucial. Why? Because now remember this problem. Okay, I'm trying to solve this. Now I'll go back a little bit and show you a node arc incidence matrix. Here it is. Yeah. For this graph here, this thing is my A. Now look at the columns. What happens if you add them up? This matrix, can this matrix have full rank, which is minimum of number of rows and columns? Like, my number of nodes is 4. Up until now in our simplex algorithm, we did have m basic variables, right? But now my mth row can be a row of zeros. Just add them up, yeah? So the matrix cannot have m as its rank. So this brings us to here. So this n minus 1 was actually important when I was actually saying. So our rank can be at most n minus 1. And it is n minus 1 because we can find spanning trees, and spanning trees will be linearly independent of each other, spanning tree columns. Then, all right, we're not full rank, but we will have n minus 1 as our basic variables. So we will have m minus 1 basic variables, which are actually the columns of the arcs representing the spanning tree. Any questions? Okay. So we have derived all the way through that a basis for a MCNFP problem will be in the form of a spanning tree. Good. Okay, then. Let's start to form our BFSs and go for our algorithm, right? Okay. Remember simplex and remember the idea, remember the things we were doing. We were the very beginning, before we start the algorithm, we were selecting m columns. First, we were trying to see if they're linearly independent or not. And if they were, if B inverse exists, then we have a basic solution. What was the thing that makes it basic feasible? We could calculate B inverse B. And if everybody was non-negative, then we were saying that, okay, this basic solution is also a basic feasible solution because it does satisfy my AX equal to B, yes, and also X non-negative. All right, that was the difference between a basic solution and a basic feasible solution. Now, a basic solution for MCNFP will be each spanning tree. All right, okay. But not all of them will be feasible, of course, right? We have bounds on our arcs. So we have to check the the values of the arcs. How much flow am I supposed to send through this spanning tree so that I satisfy my AX equal to B constraint, right? Remember, and that means, well, once you determine your spanning tree and your co-tree arcs, you could easily calculate the flow on the arcs by just looking at the B's, the supplies and demands, and the arcs should satisfy them, right? Okay, so let's look at this example here. I have a plus 40 supply and minus 10 and minus 30 demand, okay? And these are the upper bounds. That's what the legend says, right? Each graph will have a legend on the right telling you what the values are. All right, this time, the thingy on the arc is the upper bound of that arc. Okay, now let's look at, it's a graph on 4 nodes. That means our basic solution will have 3 arcs, spanning 3 arcs, right? Now, for example, let me move like this a little bit because I want to show it to you. Okay, so this is my graph, yeah? 1, 2, 3, 4. Apparently, it says, okay, let's take these 3 red arcs as the basis. So these are my basic arcs. It's a spanning tree. It has 3 arcs only. And my non-basic arcs, let me draw them like this because I need them. Maybe I changed it to red. Okay, this is a non-basic arc, and this is a non-basic arc. Okay? Be careful. The last 10 minutes of Monday class, I told you that we may have bounds, and our non-basic variables can also be on their upper bounds, not just necessarily on the lower bound. In the standard simplex, all our non-basic variables were 0. But there is a bounded simplex, and your non-basic variables can also be on their upper bounds. That's what's being happening in here. It says, okay, I have 2 arcs which are not in my spanning tree. I want them to be, let 1, 4 be at the lower bound. Okay, so on arc 1, 4, I will have 0 flow. But arc 2, 4, I want it to be at its upper bound. That means on the 2, 4 arc, I will have the flow of 20. Okay, that's what it says. It could also be 0, or 1, 4 could also be at the level 30. Okay, based on those, your flow values in your normal network will change. Now I'll have to calculate what's actually flowing through the other arcs. Now let's look at here. There's only one way, all right? There is only one way. Now node 2, let's look at the node 2. Node 2 is you just start one of the leaf nodes of the tree, one of the end nodes of the tree. It's either 2 or 4 we're going to start. Let's start from node 2. Node 2 doesn't demand anything, doesn't supply anything, but it's sending 20 units to 4, right? So that 20 units should actually be coming because node 2 doesn't have anything. So it has to send 20 units to there. Now let's look at node 1 now. Node 1 is a supply for 40 units. 20 units is going to 2, then the 20 other should go the other way around because this non-basic arc has 0 value there. Okay, now let me come back to node 3. Node 3 demands 10 units. 20 is coming from 1, 10 is left in here, and the remaining 10 will be sent to node 4. When you look, the last node is just for check because we have one more equation than we need. That's why our rank is n-1. And so for node 4 demands 30 units, 20, 10, 30. I'm safe. Okay? So these are the values of the flows. These are the x's on the graph. Okay? Now the question is, okay, so I did solve x equals b inverse b minus, I did solve ax equals to b corresponding to this spanning tree. So I have devised 1, 4 as 0, 2, 4 as 20, and I solved for the rest of the variables. Apparently, I find 1, 2 should be 20, 1, 3 should be 20, and 3, 4 should be 10. Now, is this feasible? This is a basic solution, yes, but is it a basic feasible solution? The answer is already written there, so I cannot wait for you to answer this. It is not a BFS. Why? Because this arc here, this one, I'm sending 20 units, but the upper bound of that arc is 10. So I'm over the bound. I should not be doing this. Okay? So this is a basic solution, yes, but it is not a basic feasible solution. Clear? Or do we have any questions? You guys are very silent today.
Hocam, can you please once again explain how you draw that second tree again?
How I draw the tree? I will teach you how do we find the spanning tree. Now, you remember in the very first, before we start simplex, we were selecting random columns. And if they are linearly independent, we were saying, okay, these are basic. Now, are they basic feasible? So now what I did is, okay, let's pick 1, 2, 1, 3, and 3, 4 as my basis. Because now I know that they are linearly independent. These are bases. With these basic variables, now I'm left with 2 non-basic arcs. And for those non-basic variables, I pick one of them to 0. The other one is to their upper bound. I'm just making these up. This is just one option. There are many such options, right? In the algorithm, we will go through the eligible options. But I'm just trying to show you that spanning tree corresponds to a basic solution. And how do we check if it's a basic feasible solution or not? Okay?
Okay, thank you.
Thanks, Elif. All right, then. So spanning tree is a basic solution. And for each basic solution, we check its feasibility by checking the values on the axis, what they're supposed to be, right? Now, okay, let's go on. Another option. Now it says, okay, in the same, no, it's a different graph. I want 3, 4, and 1, 4 to be non-basic. Okay, let me go back, draw another graph for you because it's 1, 2, 3, 4. This is my graph, right? 3, 4 will be non-basic. 3, 4 will be non-basic at the lower bound. It's going to have 0 flows. And 1, 2 will be non-basic at the upper bound. Okay, the upper bound of 1, 2 is 10. That means my remaining arcs will be basic, but I don't know their flows yet. I have to find and see if they are feasible or not, all right? Non-basic arcs, I'm picking. The basic arcs I have to find by this flow balance constraint. Let's look from 2 again. 2, remember, is a intermediate node, no demand, no supply. Anything in should be out. So 10 is coming in. That 10 should be going out. Okay. Node 4 requires 30 units. This one is sending 0. This one is 10. So I need 20 here. Okay. Node 1 can send 40 units. 10 here, 20 here means 10 in here. And the last node is always for you to check. Node 3 requires 10. It has 10, yes, okay. Flow balance is satisfied. AX equals to B. With these blue and red flows on the arcs, red ones are my non-basic ones, blue ones are my basic ones, flow balance is satisfied. Now I'm checking if X is between the bounds, greater than 0, less or equal to upper bound. The arc 1, 3, the upper bound is 50, so check. 1, 4, upper bound is 30, check. 2, 4, 10, upper bound is 20, check. Yes, this is a BFS. Now I did find a BFS. Okay? It's basic because it's tree, and it's basic feasible because every flow is within the bounds. Now then, I'll check if it is optimal or not, right? Now this is a basic feasible solution, which is a legitimate solution for optimality. Remember the simplex algorithm. My optimal solution will be one of those BFSs, right? Any questions? Okay. Given the non-basic values, non-basic arcs, and their values, the basic values should easily be calculated by using the flow balance constraints, AX equal to B. Okay, don't forget that. All right. Now, is this optimal? Optimality check. Rho 0. Yeah? Is there any improving direction? Or is any of my neighboring spanning trees better than this one? Or is this optimal? How do I check optimality? So what is the iteration in here? Simplex iteration. Okay, this is a BFS. Now, if I were to write the simplex table for this, this would be one of my tables. All right, fine. Now, I have to go and see my Rho 0 if there is any negative entry. If so, that would mean that, okay, I want to enter the basis, and then I'll do ratio tests, right? So that is my iteration. Now, how is an iteration in network simplex? Remember in the simplex method, our non-basic, we were checking the non-basic variables if they want to enter to the basis or not. That's what we're going to do in here. We're going to check our non-basic variables. What are our non-basic variables? The ones not in my spanning tree. So here, for example, these red arcs. These are the ones not in my spanning tree. Do they want to enter to the basis? Is it better if I have them with different values? Because I cannot immediately say I'm going to increase the value because this guy is the upper bound. I cannot increase its value. I have to be very careful at each iteration. All right. Depending on, so I'll check. First of all, in the network simplex iteration, you're supposed to check for all non-basic variables. So here I have two. I have to check these two arcs and see if it will be better for me if I change their status and put them in my spanning tree. Of course, remember, when I put an outside arc to my spanning tree, I will create a unique cycle. I don't want cycles in my basic solutions. They are linearly dependent to each other. So when I put an arc, I create a cycle. That means I have to delete one arc from that cycle so that I don't have a cycle at the end, so that I remain to have a spanning tree. Okay? That's one thing. When I look at one arc, that arc will create one unique cycle, and only that variables in that cycle will be affected. And that brings to my ratio test. Remember, I find an entering variable. Now I have to find a living variable. Now the valid entries in the ratio test are the ones in the cycle created by this arc that I'm trying to put in to my solution, to my spanning tree. Let's check. It's easier. Let's check arc 3, 4 first. Okay. Okay. Arc 3, 4. It is a non-basic arc. Yes. So when I put this arc into my solution, I do create a cycle, this one. You see, there is a cycle in here. 1, 3, 3, 4, 1, 4. That is a cycle. I don't want that. Now, that means I have to delete either this guy or this guy from my spanning tree. One of them has to be out. This is my ratio test then, okay? Which one should leave if this guy is entering? Now, you need to see what's going to happen if this arc enters to my spanning tree. This arc is like this, and currently it has zero flow. Now, first thing to check is, should I increase the flow or shall I decrease the flow? This is that value 0. I cannot decrease it. That means I'm going to send some amount from here. Some amount. I don't know. I'll determine, right? This is my ratio test, right? So first of all, this is the ratio. This is my cycle direction. This is very important. The direction and then the ratio, all right? Arc 3, 4 is currently at 0 level. If I want to put this guy into the bases, into my spanning tree, I have to increase its flow, okay? That means the cycle that it's going to create will be in the direction of that arc. So I'll send delta units from here. Now I have to remain satisfying AX equal to B, flow balance. If this is sending delta units to 4, 4 is also receiving from here and here, right? If delta is coming from here, this 2, 4 is not in the cycle. So it shouldn't be touched. But 1, 4 is in the cycle. So that means if delta is coming from 3, 4, 1, 4 should send delta units less, because 4 is requiring 40 anyway, right? So this one will be minus delta. 20 minus delta will be over the arc 1, 4. Okay. Now let's look at the node 1, flow balance of node 1. Now node 1 can send 40 units. If this guy from here, if it is sending 20 minus delta, this 10 is not touched because it's not in the cycle. This part should be sending 10 plus delta, so that overall it will send 40 units, the flow balance. And then 3 will have 10 plus delta, 10 will remain in here, and delta will go to 4. So my flow balance will be satisfied. So that means once you choose your cycle direction, that is, if it's improving, we're going to choose it. I'll explain it in a minute. But how much units can you send over this cycle direction is determined like this, all right? Depending on if it's in the lower bound or the upper bound. Okay. On the other hand, now, if I choose, let me draw it in here. 1, How was it? 1, 2, 3, 4. 1, 2, 3, and 4. My cycle was this. Is this my cycle? Hold on. Yeah. My cycle was this. So this is the cycle. This is sending 10, 20, 10, right? These were my other arcs. This was sending 10, and this was sending 0. Yeah? Oh, you don't see my screen. I did something else, but you don't see it. I have to stop sharing the screen and start sharing it again in a minute. Wait, hold on. Because I'm already in page 3, but you don't see it. Stop sharing. All right, I'll start sharing again. My iPad. Share it again. Okay. Yeah. Okay. I was doing this actually, but you didn't see that. All right. Now, so in the previous slide here, we have seen what's going to happen if we want to put the arc, which is already in its lower bound, to our spanning tree. We will send delta units in the direction of the arc, and we will look at the cycle. So if this is delta, this is reverse minus delta, plus delta, plus delta. Okay? You just look at the cycle and see what happens in the cycle. Now, if the arc is in the upper bound, this one, this is 10. It's already sending 10 units, all right? I cannot send more. That means I have to decrease the flow over there, right? So that means I have to do a minus delta there. If that guy wants to enter my tree, I cannot increase its value. I have to decrease its value, right? Well, if this is a minus delta, that means I'm sending minus delta over here. That means a plus delta in here. This is sending more, and this is sending less. In the same idea. So my direction is like this, cycle direction. Okay? So I'm sending delta units over the cycle direction if for each arc that's trying to enter, all right? Cycle direction, if the arc is in the lower bound, cycle direction is the direction of the arc. If the arc is in the upper bound, cycle direction is the reverse direction. That's all right? So that's how we determine the cycle direction. And these deltas will help us in the ratio test. Now, the cycle direction is going to help us in choosing the arc that wants to enter, if it's going to be improving or not, which arc is improving and which arc is not. Okay? Here, let's look at this example. All right. This is the same example we keep on working. 1, 2, 3, 4, right? Okay. Here is this the flow that we already have from 1 to 2? No, it's a different flow then. Okay. Let me also have it in here just in case. So 1, 2, 3, and 4. I'm checking the time. I don't want. Oh, okay. Okay. Let me just draw it. Then this is it says CUX. Okay, here's the legend. Then X is whatever is here, right? So I have 20 units in here, 10 in here, 10 in here. Apparently this guy, let me again use the red, is a co-tree arc, and this is again not spanning, not in my spanning tree. This one is sending 0 units. This one is sending 10 units. Okay. If I actually let's calculate these values. Let me not give them to you, and let's calculate them. I know the B's, right? So this one should send 20. This is a 0. This is a 0. This one should receive 20. All right. Now let's find. There is a 10 coming from arc 3, 4. One requires a 20. So the other 10 should be coming from here. Okay. Can I do these arcs? No, because there are 2 options. I don't know them yet. Let me come back here. This one is a 0. 10 is going out for 3. 0 is coming from 1, 3. So that 10 should be coming from here. There is no other way. Yeah? Okay, now I'm ready for node 2. 20 is going out from node 2. So I have to have 20 coming in because 2 is not a demand nor a cycle. And the last node is for the check. Node 1 is a supply for 20. It's sending that 20 for over the arc 1 too. So yes, this is my basic solution. Is it feasible? Let's check the bounds. The bound on arc 1, 2 is infinity, fine. The one on 2, 4 is 40. I'm sending 10, fine. 2, 3, upper bound is 30. I'm sending 10, fine. So this is a BFS. It already says, but okay, this is a BFS. The cost of current solution is, let's calculate, C times X. So 6 times 20 plus 4 times whatever is sending there, 10, plus 13 times 10, plus 5 times 10, because it's already flowing from there too. So the overall cost of this current BFS is 340. Now, is it optimal? Shall I increase? Shall I decrease any flows? I have 2 arcs, arc 1, 3, and arc 3, 4, that I have to check. But I'll do it in the next hour.